What if I told you the moon is slowly escaping Earth, and we can measure it with lasers accurate to the width of a human fingernail? Right now, as you're reading this, the moon is drifting away from us at about 3.8 centimeters per year. Roughly, the speed your fingernails grow. It may not sound dramatic, but over millions and billions of years, that tiny shift adds up. The sky looks stable, eternal, unchanging, yet that calm white circle has been silently moving farther away for about 4.5 billion years. During the Apollo missions between 1969 and 1972, astronauts placed special retroreflectors on the moon's surface. Scientists still fire laser beams from Earth at those mirrors and measure the return time with extreme precision, confirming the moon's gradual retreat. This slow escape is caused by tidal forces. Earth's rotation creates ocean tides that transfer energy to the moon, pushing it outward, while Earth's day lengthens by about 1.7 milliseconds per century. Hundreds of millions of years ago, a day on Earth lasted only about 22 hours. In the distant future, total solar eclipses will disappear because the moon will appear too small to fully cover the sun. This isn't science fiction. It's orbital mechanics, measurable physics, and it's happening right now. Number 1. The moon is receding every year. The moon is moving away from Earth at a rate of about 3.8 centimeters per year, roughly the speed your fingernails grow. And while that sounds tiny, over cosmic time, it becomes staggering. In just 100 years, the moon shifts nearly 4 meters farther away. In a million years, that's about 38 kilometers. Over a billion years, nearly 38,000 kilometers. A distance greater than Earth's entire circumference of about 40,075 kilometers. Scientists measure this drift with astonishing precision, thanks to retroreflector mirrors placed on the lunar surface during the Apollo missions between 1969 and 1972, as well as by Soviet Lunokhod rovers. Powerful observatories fire laser pulses at these mirrors, and by timing the round trip of light, which travels at 299,790 kilometers per second, researchers can calculate the Earth-Moon distance to within a few millimeters. The current average distance is about 384,400 kilometers, though it varies because the Moon's orbit is slightly elliptical. The reason for this slow escape is tidal interaction. Earth's rotation creates ocean bulges that transfer angular momentum to the Moon, pushing it outward while slowing Earth's spin. As a result, our planet's day lengthens by about 1.7 milliseconds per century. This isn't speculation or theory. It's physics confirmed by decades of laser measurements, the orbital mechanics, and precise astronomical data, proving the Moon is gradually, measurably drifting away every single year. Number 2. Tidal forces are stealing Earth's energy. So what's pushing the Moon away? The answer lies in tides and the precise physics of angular momentum. The Moon's gravity pulls on Earth's oceans, creating 2 tidal bulges, one facing the Moon and one on the opposite side. But here's the crucial twist. Earth rotates once every 24 hours, while the Moon takes about 27.3 days to orbit us. Because Earth spins much faster, the tidal bulge doesn't line up perfectly under the Moon. It gets dragged slightly ahead of it. That offset bulge exerts a forward gravitational pull on the Moon, transferring energy and angular momentum into its orbit. The result: the Moon gains energy and moves into a slightly higher orbit, increasing its average distance of 384,400 kilometers by about 3.8 centimeters per year. In exchange, Earth loses rotational energy, causing our planet's spin to slow. Scientists have measured that Earth's day lengthens by roughly 1.7 milliseconds per century due to this process. Hundreds of millions of years ago, a day lasted closer to 21 to 22 hours, and fossil coral growth rings confirm that there were over 400 days in a year during the Devonian period around 400 million years ago. This ongoing gravitational exchange is governed by conservation of angular momentum, a fundamental law of physics, and it has been reshaping the Earth-Moon system for over 4.5 billion years. Earth is slowly paying the price, 1 millisecond at a time. Number 3, Earth's days are getting longer. Because Earth is losing rotational energy through tidal friction, our planet is spinning more slowly, and the length of a day is increasing by about 1.7 milliseconds per century. That may sound insignificant, but over geological time, it becomes dramatic. High-precision atomic clocks, combined with historical astronomical observations, confirm this gradual slowdown, and the fossil record independently supports it. Ancient coral fossils from the Devonian period, around 400 million years ago, contain microscopic daily growth rings that function like natural calendars. By counting these rings, scientists have determined there were roughly 400 to 420 days in a year at that time, meaning each day lasted only about 21 to 22 hours instead of today's 24. Even older tidal rhythmites, layered sedimentary rocks shaped by ancient tides, tell a similar story, preserving patterns that reflect shorter days and more frequent tidal cycles hundreds of millions of years ago. This evidence shows Earth once rotated significantly faster, completing more spins per orbit around the Sun. The reason is tidal interaction. As the Moon pulls on Earth's oceans, friction between water and the seafloor dissipates rotational energy as heat, acting like a cosmic brake system. Over 4.5 billion years, this steady gravitational exchange has slowed Earth's spin while pushing the Moon farther away, reshaping the dynamics of our planet 1 millisecond at a time. Number 4. The Moon was once terrifyingly close. Billions of years ago, shortly after its formation about 4.5 billion years ago, the Moon was dramatically closer to Earth. Some models suggest it may have orbited at distances as small as 20,000 to 30,000 kilometers, compared to today's average of about 384,400 kilometers. That means it could have appeared more than 10 times larger in the sky than it does now, dominating the horizon in a way almost impossible to imagine. At such close range, tidal forces would have been immensely stronger, potentially hundreds of times more powerful than modern tides, generating massive tidal bulges and extreme coastal flooding across the young planet. Early Earth rotated much faster, possibly completing a full day in as little as 5 to 10 hours, which would have intensified tidal cycles even further. These enormous tides likely played a major role in shaping early coastlines, driving ocean mixing, influencing volcanic and tectonic activity, and possibly creating tidal pools where complex chemistry linked to the origin of life could have developed. Over billions of years, through tidal friction and conservation of angular momentum, the Moon migrated outward to its present distance, transforming from a dominant gravitational force looming overhead into the smaller, steady companion we see today. Yet it continues to shape Earth rotation, climate stability, and ocean dynamics even now. Number 5. One day, total solar eclipses will end. Right now, we live in a remarkable and temporary cosmic coincidence. The Moon appears almost exactly the same size in our sky as the Sun, although the Sun's diameter is about 1.39 million kilometers, roughly 400 times wider than the Moon's 474-kilometer diameter. It is also about 400 times farther away, at an average distance of 149.6 million kilometers, compared to the moon's 4,400 kilometers. This near-perfect ratio allows the moon to precisely cover the sun during total solar eclipses, briefly revealing the sun's corona in a spectacle that can last up to about 7.5 minutes. But this alignment is not permanent. Because the moon is drifting away at about 3.8 centimeters per year, its apparent size in our sky is gradually shrinking. In roughly 600 million years, it will no longer appear large enough to completely block the sun. Total solar eclipses will disappear, replaced only by annular eclipses, where a bright ring of sunlight remains visible around the moon's silhouette. Geological records suggest that billions of years ago, the moon appeared much larger, producing longer and more frequent total eclipses. Humanity exists within a relatively narrow window of cosmic timing, a few 100 million years in Earth's 4.5 billion year history, when perfect total eclipses are even possible, making our era astronomically special. Number 6. The moon stabilizes Earth's climate. The moon does far more than control tides. It plays a crucial role in stabilizing Earth's axial tilt, which is currently about 23.5 degrees and responsible for our seasons. This tilt determines how sunlight is distributed across the planet throughout the year, shaping climate patterns, ecosystems, and even the development of agriculture and civilizations. Earth's large moon acts as a gravitational stabilizer, reducing chaotic variations in our planet's obliquity over long timescales. Computer simulations show that without the moon, Earth's tilt could vary wildly, potentially shifting between 0 and 60 degrees over millions of years, leading to extreme climate swings. Mars offers a real example. Lacking a large stabilizing moon, its axial tilt fluctuates dramatically between about 10 and 60 degrees over geological time, contributing to severe and unpredictable climate changes. Earth's relatively stable tilt has helped maintain a more consistent climate for hundreds of millions of years, supporting the long-term evolution of complex life. However, as the moon continues drifting away at 3.8 centimeters per year, its stabilizing influence very gradually weakens. While any major instability would take billions of years to develop, this slow orbital migration subtly alters the gravitational balance that has helped keep Earth's seasons and climate comparatively steady for much of its 4.5 billion year history. Number 7. A future of mutual tidal locking. If given enough time, Earth and the moon would eventually become mutually tidally locked, meaning each would always show the same face to the other. The moon is already tidally locked to Earth. It rotates once every 27.3 days, exactly matching the time it takes to orbit our planet, which is why we only ever see one hemisphere. This synchronization happened billions of years ago due to tidal friction, dissipating the moon's rotational energy. The same physics is slowly acting on Earth. As tidal forces continue transferring angular momentum to the moon's orbit, Earth's rotation keeps slowing by about 1.7 milliseconds per century. In a fully tidally locked state, a single hemisphere of Earth would permanently face the moon, and a day on Earth would last as long as the moon's orbital period, which by then would be much longer than today's 27 days, because the moon would be farther away. However, calculations suggest this process would take tens of billions of years to complete. The Sun, currently about 4.6 billion years old, is expected to enter its red giant phase in roughly 5 billion years, likely engulfing or dramatically altering Earth before full tidal locking could occur. In other words, while the physics points toward an eventual Earth-Moon synchronization, the ultimate fate of the system may never fully unfold before the Sun reshapes it entirely. Number 8. The sun will interrupt the process. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core and expand into a red giant, dramatically transforming the inner solar system. But Earth's habitability will decline long before that final expansion. As the sun gradually brightens, increasing its luminosity by roughly 10% every billion years, climate models suggest Earth could experience a runaway greenhouse effect in about 1 to 1.5 billion years, evaporating oceans and ending surface life as we know it. When the sun fully enters its red giant phase, its radius could expand outward to roughly 1 astronomical unit, about 150 million kilometers, the current distance between Earth and the Sun, Mercury and Venus, will almost certainly be engulfed. Earth's fate is less certain. Some models suggest it may be swallowed, while others propose it could spiral outward slightly due to solar mass loss, though intense heat would render it completely uninhabitable regardless. During this time, the Moon will still be drifting away at about 3.8 centimeters per year, but its gradual escape will be overshadowed by the Sun's far more violent evolution. The slow tidal dance between Earth and the Moon may never reach its theoretical end state of mutual tidal locking, because a much larger cosmic transformation, the death of our Sun, will likely intervene first, reshaping or destroying the Earth-Moon system entirely. Number 9. The Moon was born from catastrophe. The leading scientific explanation for the Moon's origin is the giant impact hypothesis, which proposes that about 4.5 billion years ago, a Mars-sized protoplanet called Theia collided with the young Earth. This catastrophic impact released an enormous amount of energy, likely vaporizing large portions of both bodies, and ejected vast quantities of molten rock and debris into orbit. Over time, that orbiting material coalesced under gravity to form the Moon. Evidence supporting this theory includes the Moon's relatively small iron core compared to Earth's, and the striking similarity in isotopic composition between lunar rocks and Earth's mantle, confirmed by samples returned during the Apollo missions between 1969 and 1972. Computer simulations show that such an impact could also explain Earth's 23.5-degree axial tilt and its rapid early rotation, with days possibly lasting just 5 to 10 hours. Ironically, the same collision that gave Earth its Moon also set the conditions for its gradual escape. The newly formed Moon began orbiting much closer, perhaps only 20,000 to 30,000 kilometers away, generating extreme tidal forces that transferred rotational energy from Earth to the Moon. That ongoing tidal interaction, governed by conservation of angular momentum, is what still pushes the Moon outward today at about 3.8 centimeters per year. The Moon's existence and its slow departure both began with cosmic violence. Number 10. The Earth-Moon system is still evolving. We often think of the solar system as stable, balanced, and finished, a perfectly arranged clockwork that has always looked the way it does now. But in reality, it is dynamic, constantly evolving under the laws of gravity and motion. The Moon's slow recession, at about 3.8 centimeters per year, is measurable proof that even the most familiar object in our sky is part of an ongoing gravitational exchange. That tiny drift is tied to Earth's rotation slowing by roughly 1.7 the milliseconds per century to tides transferring angular momentum, and to a system that has been reshaping itself for 4.5 billion years. Hundreds of millions of years ago, days were shorter. The Moon appeared larger, and total solar eclipses lasted longer and occurred more frequently. Hundreds of millions of years from now, total eclipses will vanish entirely as the Moon appears too small to fully cover the Sun. Over geological timescales, Earth's climate stability axial tilt behavior, and ocean dynamics are all influenced by this delicate interaction. Even planetary orbits across the solar system subtly shift due to gravitational perturbations between planets. The night sky feels permanent because human lifespans are brief, measured in decades, not billions of years. But permanence is an illusion. The cosmos is not frozen. It is a slow-motion story of motion, energy transfer, and inevitable change. The moon looks calm, silent, eternal, but it's moving away from us right now, centimeter by centimeter, and we are living in a temporary moment of perfect balance in a system that never stops changing. If this blew your mind, imagine what else the universe is quietly doing above us. Like this video, subscribe for more real space mysteries, and remember, the sky is not as stable as it looks.